So let's move on to Module 7's quadratic functions for this lesson. So we're going to take a look at what's the definition and what are the properties of quadratic functions. First of all, we start off with a quadratic is any equation that has the properties or has a form, has an x squared in it, and some number times an x, and then there could be a constant term. So the a, b, and c's are really not variables, they're real numbers, and the definition must be that a does not equal 0. Because if a were 0, then there'd be no x squared, and that's what we called a linear. So all of this together gives us a quadratic function, and we're going to see it gives a particular shape to the graph. It has because of the squared function, it will either open upwards or downwards. And the way we can tell the difference is what the value of a is. As long as a is a positive value, it's greater than 0, then you will see a parabola which opens upwards. In calculus, we call this concave up. We also say it can hold water. So we put water in here, it's like a glass. So it's opening upwards. Conversely, if, the other part we're going to see is important part of quadratic functions is then in this case we have a minimum value. The vertex is the minimum value, it's the lowest value on the graph. Conversely, if the first coefficient of the leading term, the a value, is negative, if it's less than 0, that's, as we saw with the reflections and the translations and the transformations, so it would be a reflection. It would reflect it over the x-axis, right? And so we've got something that opens downward, or in calculus we call this concave down, because if it would, one way we say is it would spill water. If you try to keep water, no water's not going to stay, it's going to fall out. So it's a glass that's upside down. It also gives us something that's important here. It gives us a maximum value, maximum y value at the vertex. And again, if it's just this function, negative x squared, it happens at the origin. But what we're going to see is as we take a look at the full force of a quadratic function, that vertex can move and be in different places, not just the origin. So that's kind of getting us set up so far. We've got something else we'll highlight here while we're here, do a little bit more, is that with quadratic functions, where the vertex is, there's also something called a line of symmetry. We talked about this when we were talking about even and odd functions. In this case, the line of symmetry for these two particular functions, because they're just at the x squared or the minus x squared, is going to be the y-axis, or the line x equals 0. That's the vertical line. X equals 0 is what we call the axis of symmetry. So that will be another thing that enters into our discussions of quadratic equations, quadratic functions. The best way to tell the domain and range of a quadratic function is to take a look at its graph, but also to have, if you have the vertex, you have a lot of information. Because remember, the vertex is either a maximum or a minimum, depending upon whether it opens up or down. And again, that's why if we just look at the graph of something, it makes it so much easier. So we can see with this graph, we can highlight the point of the vertex. We know that as given is the point 0, 1. And so we see that, first of all, we can see, as we will see with all quadratic functions, that because they shoot off in both directions, Now it looks pretty steep, but they're going to keep going um, in the x direction at least forever. So the domain is always for every quadratic function is going to be every quadratic function domain is going to be negative infinity to infinity, all real values. Kind of like we talked about, you can put anything in for an x squared and it'll come out. But the range is graphically, as we're going to see here, um, is from either the vertex up or the vertex down. And from this one, we can see it's from the vertex downward. So 1, the y value of the vertex, that's going to be the largest value. And that is included, right? It is a point on the graph. And then it's going to go down to negative infinity. Okay, so I kind of got it backwards because we always have to list it from smallest to larger. Sometimes it's helpful if we kind of look at this as a number line thing. Okay, so it's going down to negative infinity. Got to go from smallest to largest. So we start at negative infinity and we can come all the way up to 1. That will be our range. Okay, so just watch that. Sometimes I'll see this notation 1 to negative infinity, but the order always has to be from smallest to largest. Okay, so that's all we were asked for here is the range and domain. Again, if we wanted the axis of symmetry for this particular one, we can see the vertex, the x value of the vertex is 0. The y-axis is the axis of symmetry, and so we say that x equals 0. That's the equation of the y-axis, is the axis of symmetry. Okay. And we've done this using interval notation. So let's just kind of take some time and explore what we can have happen with another quadratic function. This time a little more interesting than just an x squared function. We're going to consider the quadratic function given here. So one of the things we could do is, it's always good if we can always use our graphing calculator or use Desmos, as what I like to do is use Desmos. And we're going to, by looking at the graph itself, we'll see some connections between what this function looks like and the graph itself. So let's go ahead and go over, we'll keep these for now. Let's go here and we'll go to Desmos. Calculator, which brings us to the graphing portion. And let's just put in a function. Let's go with f of x. What did we have? We had x, is it x plus 3 or x minus 3? X plus 3. Of course, I end up revealing. So x plus 3, then the parentheses, then the square, just 1. Okay. And then we are going to subtract 2. Make sure I get that right. Yes, subtract 2. And one of the things we can see right away is, that's what's nice with Desmos, is we can find the vertex by just clicking on that point there. So we see it's giving us a minimum. First of all, we do see that x is positive, so when we square it out, we could implicate that that's going to give us a leading coefficient on the x squared of a positive value, so it should open up, which it does. Notice the value of the vertex is related to these numbers that we have here, but it's the opposite of the 3. It's a negative 3, but negative 2. So we're subtracting 2, and that gives us the y coordinate is negative 2, but the x coordinate of the vertex is the opposite of what appears in this format. And we're going to see we call this particular format of a quadratic function the vertex form, because you can actually see the vertex right there. Okay. Some of the other parts we're going to want to pick up is we're going to want x-intercepts. So these don't have integer values, which is fine, but those are two things. But what you'll see is that the x-intercepts are symmetric about the vertex. So what we're going to see here is we wanted to an axis of symmetry comes through here right at negative 3. Right? So there's our axis of symmetry, x equals negative 3, going right through the vertex. The other thing is you could actually draw that, have Desmos draw it. That's the vertical line x equals negative 3. And we see that if we hold down on this, no, it's not going to work for me. Negative 3. You could also change it to a dashed line and so forth. Okay, so we've got an axis of symmetry there. Cutting through from the graph, we can pick up our x-intercepts. We can also pick up the y-intercept, which is not as obvious. We'd have to actually FOIL this out, but we could pick that up there if needed. Okay. The other way we could get that y-intercept, notice the y-intercept always has an x value of 0. So we plugged in 0 for x. What are we left with? We're left with just 3. 3 squared is 9. 9 minus 2 is 7. So you could come up with the y-intercept that way. But again, just as sort of an exploration, we can take any quadratic function. The main thing we're going to be focusing on are things finding the axis of symmetry, which is given to us once we know the x-coordinate of the vertex. The range is given to us by the y-coordinate of the vertex and whether it opens up or down. And then the other important parts are x-intercepts, because that's where y equals 0. So those are oftentimes important parts of the problem we're solving for. Sometimes the y-intercept's important, again, because that's sort of a starting place. So there's what I say is I call these four of the important points, because if we know each of these 4 points, we know a lot about this parabola. We can answer many questions, not necessarily all of the questions, but we can answer quite a few of them. Okay, so let's kind of just clear this out, and we'll go back to our presentation. So this is our vertex form. Notice that on the particular one we have, on the particular function we have, there is no value in front of the parentheses. That actually would be a 1. Okay, so that's that a value. It could be 2 or 3, and what this number in front is going to be, if you remember from transformations, it will be either it causes a vertical stretch or vertical compression, because it's on the outside of the function. So this is a stretch or shrink. Okay, So in some cases we need it, but the important part is that when we have it in this form, then we've got the vertex. Um, when they use the vertex form, notice they put the negative. So this is something we can, so I see it's +3, so I know it's going to be a -3. So how did that become +3? Because if we use the formula, it would be x minus -3 squared minus 2. And then now I know the vertex is -3, -2. If I had another one that was, say, x minus 4 squared, kind of the way I was doing it, well, it's got to be the opposite of the sign, right? So it's going to be, the vertex is going to be at +4, and whatever y value is out here, if this is, say, +2, then it would be at 4, 2. Okay, so the vertex form is, the definition of it is given with a negative in here, so that we don't have to remember necessarily to change it, but sometimes that causes the confusion. So the negative should be out here. So if it is negative, then the answer of the vertex is positive. If it's positive, then you must have had a negative on the x coordinate of the vertex to make it work. Okay, so hopefully that makes some kind of sense. And then finding special points on the parabola, we can look at a few examples. And those special points, as I mentioned, were the x-intercepts, the y-intercept, and the vertex. So finding the x-intercepts and the coordinates of the vertex for the parabola. For me, what I like to do is go ahead and just graph it, because those are going to be given to us, which we'll do in a moment, just like I showed you. So, but I also want to show you there's another way to go about this. So let's look at the x-intercepts. Remember, the x-intercepts are places where the y-coordinate is 0. Okay, so y is going to be 0. So we've done this earlier. We can basically just solve this for x when y is equal to 0. Now sometimes it'll work, this will factor. Sometimes it's a little harder, but okay, so one thing we can do is to solve this, to make it a little easier, because these negatives may throw us off, is we could multiply both sides by -1. Because I think we'll get this to factor, and we'll see this. So if we do that, -1 times 0 is still 0, and we get x squared plus 8x plus 16. This does factor. Let's come up here, because I want to save some room down there. Factors into x plus 4 and x plus 4. 4 times 4 is 16. 4x plus 4x gives us our 8x. So if you FOIL it out, you'll see that that works. And so then we get that either x plus 4 equals 0, or x plus 4 equals 0. So we see we're really only going to get one answer for this x-intercept. So that gives us, subtract 4 from both sides, right? Gives us that x equals -4. Two values of that. So that gives us an x-intercept. Okay. One of the things we're going to see when you only have one x-intercept, the only way for that to happen, this is happening out at -4, I'll put this over here at -4. The only way for that to happen is for the parabola to come up and touch the graph. So what you're going to see is that this x-intercept is also going to be the vertex. Okay. And the reason I know it opens downwards, again, from the original function, there was a negative here. I know it's opening downwards. I know that there is only one x-intercept. The only way that can happen with a U-shaped deal is for the parabola to just sort of, as I say, sort of kiss the x-axis. So this is the point -4, comma 0. So we've also got our coordinate for the vertex. And the x-intercepts, -4, 0, all in one kind of roll. So that's kind of a cool thing to do. I'm going to show you one more way of getting the vertex. One way to get the x-coordinate for the vertex when it's in this form is there's a formula. So for the vertex, this comes from the quadratic formula itself. The x-coordinate is going to be minus b over 2a. So that's the first part of the quadratic formula, and then there's a plus or minus square root thing. But if you just remember that first part actually gives you the x-coordinate. And let's see if that works. So minus b, in this case, is -8. A is -1. So let's plug those in. So we get a minus from this, and then we're plugging in -8. We get 2 times -1. And so a negative and negative is a positive, so that's 8. A negative in the bottom gives us a -2. 2 divided by, sorry about that, 2 divided by, or sorry, 8 divided by -2 is going to give us -4. So we see that x equals -4. So this is something, again, it's in the notes, but this is going to be a valuable way to find the vertex. And then what we would need to do is take that -4 to find the y-coordinate, plug it in for x, and then what we would see in this case, it's going to be equal to 0. So let's go ahead and do that just to take this one more step. So we would take negative, and then in the x, we're going to plug in -4. We're going to square that. Oops, we've got -8 times -4 minus 16. So -4 squared is 16, then we put a negative on it. So we end up with -16. -8 times -4 is a positive 32. Let's do it over here. Sometimes on my screen, some places want to work and some don't. And then we've got the -16. If you add all that together, you get 0. So the vertex, x is -4, y is 0. All right. Let's take a look at another one. As I said, I wanted to reserve some space down here. Let me erase a little bit of what I did. This stuff didn't use it anyway. Make it cleaner. And this is another example that's a little more complicated. So let's put that back there. Because it doesn't factor, and so we want to find the coordinates of the vertex and the parabola and the x-intercepts. So again, for this one, does it factor 3 times 5? It might factor. It actually might factor. But in this case, let's go ahead and take a look at what it would graph as. So then we'll just do y equals, and we'll put in minus x. We know it's going to open downward because of this negative. So is it plus 2x, then plus 15. And again, the nice thing is it saves us a lot of work. We can go back and check on it, but it gives us the vertex as 1, 16, just like that. 5, 0, and -3, 0. So we've got our x-intercepts, we've got our vertex. And again, if we wanted to also talk about the axis of symmetry, that comes right through here. And it's going to be the x value of of the vertex, right? So it's going to be x equals 1. That's the equation of the vertical line that cuts through there. So let's see how quickly we got our answers here. 1/16 the vertex. We just tap on those and those make those permanent. Take a screenshot if you want. It kind of shows your work, but we'll go through and we'll see how actually we're going to, this helps us see the factoring. Yeah, we'll factor into x plus 3, x minus 5. Remember the signs are the opposite when we go to the factors. And we'll be able to also pull out the vertex right from the formula itself. Actually, we could do that right here while we're here, since we're going to be here, right? So one thing is, let's go ahead and see. Let me get this out. My line has kind of moved on me. We'll just get that out of the way. So first of all, vertex. X equals minus b over 2a. So b is 2, so it's going to be minus 2. So plugging in the value for b. And then a is negative 1, so I'll put that there. So I get negative 2 over negative 2 which equals 1. And that's what I was getting over here, right? So my vertex right there. What I need to do is then plug this x back into the function. So I need to find f of 1. So that's going to give me minus 1 squared plus 2 times 1 plus 15. 1 squared is 1 with a negative plugged onto it. 2 times 1 is 2. Plus 15. So I get negative 1 plus 2 is 1. 1 plus 15 is 16. So that's the y coordinate of the vertex. So I get the vertex as 1, 16. And then I'll let you go ahead and do the factoring. So you could see that this is going to factor. What I might do is I could set this equal to 0. I don't like having negatives in front of the x squared. So I would, and the thing is, when you go to get your x-intercepts, you're going to get the same value regardless, as long as it's, because that's where y equals 0, right? So we have 0 equals negative x squared plus 2x plus 15. But I'm going to multiply everything by negative 1, which on the left side, negative 1 times 0 is still 0, so that's good. On this side, if I multiply everything by negative 1, all the signs will change. So negative becomes positive, positive becomes negative, and a positive becomes negative. And so when I go to factor this, I get my x times x. 15 is 3 times 5. Since it's a negative, it's going to be a subtraction problem. And 3 minus 5 is 2. Since the middle term is negative, I want the bigger number, the bigger value, the 5, to be negative. And you'll see that that works. And so what that does is, remember, the x-intercepts are the opposite values of these factors. So it's going to be positive 5 and negative 3. And that's exactly what shows up here. Negative 3 and positive 5. And our vertex. Okay. And again, we could, in all of this, let's go ahead and just, it's going to look a little messy, but we could put in our vertical. That's what I like about Desmos, is I can actually put this in as x equals 1. There's our vertex, or our line of symmetry at cutting the parabola right in half. Okay, so we've got one more example to look at, and we're going to do this. We're going to see how we can do some problem solving using this information. Okay. And then we'll get you working on using Desmos, being able to solve for x-intercepts and um, vertexes. Okay, so let's go with the, where Yolanda has 160 meters of fencing to form 3 sides of a rectangular field. So we can kind of see the 4th side borders a river, will not need fencing, so we don't need no fence here. We just want to fence in maybe from the deer or something, and I don't know, deer could probably swim and come up from the river, but whatever they want to do, they're not worried about the river. They just want to do the backside. So showing us here, and they define one side to be x, and so notice since it's rectangular, this side is also going to be x. The thing is the 3rd side, we and it just says to optimize the area. So we want to do this in a way. We want the dimensions for x that would allow us to have the most area in here. So remember, optimizing means to sort of maximize or minimize, and but optimize to either use the most, get the most area, or use the least material. In this case, we want to get the most area. So remember, optimization, when you see that, you're going to already be thinking vertex, because vertex is where you either get a minimum or a maximum. The hardest part of this is probably finding out how long is this side. Well, we use x and we use x, so we've used up 2x's, 2x, whatever that is. So if x was 10, we've used up 20 feet, right? 2 times x. How much do we have to use? We have 160. So if we take 160 minus 2x, that's the length of this side. This length is that. Now area is length times width, and so it's going to be this little part we got up here as our length times the width of x. So area is length times width, so that's going to be 160 minus 2x times x. Now make the full quadratic. Let's go ahead and distribute this x through, and then we'll see we do get a quadratic. So that's 160x minus 2x squared. Now with a negative 2x, we see that that's going to be a parabola that opens downwards, which means it's going to have a maximum at the vertex. So the vertex will give us a maximum. What are we getting here? Well, x is the, as we can see, the dimension, sorry, x is the dimension of one side of the fence, right? The y output here is the area, so it will give us what the actual area is. So if we find the vertex on this, we're home free. We will know the dimensions, and then we will also know the maximum area. Almost home free. We'll probably want to find this length here, because we'll have to plug, once we get x, we plug it in to figure out how much is left there. Okay, so what is the formula for finding the x coordinate of the vertex? It's minus b over 2a. So notice this one, it might be helpful if you put the c. So we've got the a, this is our a, this is our b, because it's kind of been weird, and then there's a plus 0 is what c is over here, right? There's nothing there, so that's what c is. We don't end up using c, but that's okay. So b is 160, so it's going to be negative 160. A is negative 2, so that's 2 times negative 2. So we get negative 160 over negative 4. 4 goes into 16 4 times, so that's going to be a positive 40. X is going to be positive 40. Okay, And so we could put that there. And then what's the other length going to be? Well, it's going to be 160 minus 2 times 40. So that's 160 minus 80, which is 80. Kind of makes sense. A lot of these problems, you get a nice symmetrical pattern going on. So it doesn't really tell us too many details, but what do we want? We want the length to be 80. We want the width, which is the x value. We should define our variables maybe over here, 160 minus 2x. We want the width to be 40, and that will give us an area of what? Well, we go back to our original equation here. We plug in our 40 to this. The area is going to be equal to 160 times 40, so 160x, minus 2 times 40 squared. $160 times 40, 4 times 16 is going to give us 64 with 2 zeros. 40 squared is going to be 4 squared. 4 times 4 is 16 with 2 zeros, because right, that's what ends up happening. So, and then times that by 2. So we get 1600 for 40 squared. 2 times that is going to be 3200. 64. 6,400 minus 3,200 are the area that we're going to be able to contain there is 3,200. And this is in meters, so the area will be in meters squared. There we go, meters squared. Notice that optimize refers back to the vertex because we want minimum or maximum, in this case a maximum. So that's how we can use the formula for the vertex that we've got. We can use Desmos to find quadratic, the x-intercepts. We can also use our factoring to find x-intercepts. We could also use the quadratic formula with that full square root thing. But in those cases, most of the time, we could just go ahead and find out using Desmos. Okay, so this will end our direct instruction for quadratics. Time to work on those learning activities for Module 7. Remembering to seek assistance through the online tutoring, the instructor office hours, or working with your peers in the discussion forums. And I say or, it's an inclusive or. It's doing all three of these as needed, using the one that you find helpful, but keep moving forward until you find that success.